Hello, this is section 3.3, part 2. It's called the remainder theorem, the factor theorem, and synthetic division. So what we're going to do is I'm basically going to demonstrate to you what this remainder theorem says. It says if the polynomial p of x is divided by x minus c, then the remainder is the value p of c. Okay, so here is our polynomial. And this is c equals 1. So this is a potential 0 for our demonstration. And the remainder theorem says, let's see what happens when you divide by x minus c. So if c is equal to 1 and it's a 0, then x minus 1 is a factor. Okay, so we are now set up if the polynomial is divided by this factor. So I'm going to do this using long division, but then I'm going to teach you a shortcut because we are going to be dividing linear factors a whole lot. And it turns out, since we do the same thing over and over again with long division, there's a shortcut called synthetic division. Okay, so we have the 0 was 1, the factor is x minus 1. And now we're going to divide. So x cubed divided by x is x squared. Then distribute that x squared. You get x cubed minus 1x squared. Draw your line, change the signs. And you get x cubed minus x cubed is 0. And negative 3x squared plus 1x squared is negative 2x squared. And you bring the rest down. And then start over. Negative 2x squared divided by x is negative 2x. And then you multiply that back out, and you get negative 2x squared plus 2x. Then you draw your line and change the signs. You get 1x, and then minus 1. Last time, because the degrees are the same. So we keep going until this degree is smaller than that degree. So 1x divided by x is 1. And then 1 times x is x, and then 1 times negative 1 is negative 1. Draw your line and change the signs, and you get a remainder of 0. So this is the quotient, and this is the remainder. Now, here's what the remainder theorem says. The remainder theorem says if the polynomial is divided by x minus c, then the remainder is the value p of c. So what that's saying is, let's see what happens when we put the 0, 1 in for this polynomial. So that would be 1 cubed minus 3 times 1 squared plus 3 times 1 minus 1. And I'll use the calculator for this. So parentheses 1 cubed minus 3 times 1 squared plus 3 times 1 minus 1. When we hit enter, we get a remainder, we get a value of 0. So that's the same remainder that we got when we did long division. So what the remainder theorem says is if you want to test a 0 really quickly, you don't have to divide. You can test a 0 by just putting that 0 in, and whatever it comes out to be is the remainder. Now the factor theorem says if the remainder is 0, then that means that 1 is a 0, and therefore x minus 1 is a factor. So this was a potential 0. Because we had a remainder of 0, this is indeed a factor. All right, now let's keep going, and then I'm going to show you synthetic division. Okay, so since this is a remainder, I always say division is a really cool way to factor, because you've got one factor that clearly is a factor if you have a remainder of 0. So that x minus 1 is a factor, and this quotient is a factor. And if we were to multiply these two together, we would get what we started with. So if you have a factor, and if you have one linear factor and you want to know what the other factors are, all you have to do is divide. All right, so now this actually is not completely factored. It turns out that this factors into two binomials, x and x. And the factors of 1 that add up to be -2 or -1 and -1. So this ends up being factorable into x minus 1 cubed. Okay, now, we don't want to be doing long division all the time, so I'm going to show you the shortcut for it's called synthetic division. And if you are dividing by x minus 1, then what you're really going to do is you're going to put the 0 in the box. So if x minus 1 is your factor and you set it equal to 0, that's what goes in the box. Then you're going to lose these variables, but you're going to put the coefficients down. Okay, so we've got 1, that's my x cubed term, and then your x squared term is -3, and then your x term has a coefficient of 3, and then your constant term has a coefficient of -1. So the coefficients go across the top. Now, since we're losing these variables in our arithmetic, you have to put a placeholder. So, for example, if this term was missing, you would have to put a 0 there to act as a placeholder for that term. Okay, so you are going to then draw a line. You skip a space and draw a line. All right, now, what's happening here, as you might have noticed, is you divide and then you multiply back out and then you draw your line and change the signs. Well, when we changed that x minus 1 to just a 1, it was kind of like we changed the signs. And so what we're going to do is repeatedly do the same thing. We're going to take that 1 and add it to nothing, and you get 1. So you always start out that way. And then to get back over the line, you're going to take that 1 and multiply it by 1, and get 1. Now you're going to do it again. -3 plus 1 is -2. So you're adding when you go straight down, and you're multiplying when you go diagonal. So 1 times -2 is -2. And then you're adding, and you get 1. And then 1 times 1 is 1. And then you're adding, and you get the remainder 0. So now what these are the coefficients, and you divided it x cubed by an x minus 1, x cubed minus divided by an x. So that means that this degree is just going to go down 1, and these are the coefficients. So we got 1x squared, and then minus 2x, it goes down 1, and then plus 1, and the remainder is 0. So now we have the same thing we had over here. We had x minus 1 is a factor, and x squared minus 2x plus 1 is a factor. So you don't have to use long division when you're trying to find if a 0 is a 0 is a 0, or find out if a linear factor is a factor. You can only use synthetic division when you have linear factors. So you still have to know how to use long division, because we might be asked to divide by something that's not a linear term. All right, let's do the second one. Okay, so we're going to let p of x equal this polynomial, and our potential 0 is 1. All right, I'm going to go at it a different way this time. I'm going to demonstrate the remainder theorem. So what I'm going to do is go it the other way. So I'm going to just put p of 1 into this and check to see what I get. So I'm putting this 1 in for x. And do you remember what it's going to show us? Let's see what we get. We get in parentheses 1 cubed plus 2 times 1 squared minus 3 times 1 minus 10. And we get p of 1 equals -10. Do you remember what that tells us? All right, well, let's see what happens when we don't have to do long division. We're going to do synthetic division. Okay, so what we're going to do is, this was a potential 0, 1. So x minus 1 is a potential factor. And we can test out whether that's a factor by using some division, but since this is a linear degree 1, I can use synthetic division. So again, x minus 1 equals 0, 1. The actual 0 goes in the box, and the coefficients 1, 2, -3, and -10. And you have to put a placeholder, so I just like to write these across top and make sure I don't have a missing term. So the x cubed term, x squared, x, and then constant. All right, So we're going to add, so that's just 1. 1 plus nothing is 1. Then we're going to multiply. 1 times 1 is 1. And so we're going to multiply when we go diagonal. Then we're going to add, and we're going to get 3. Then we're going to multiply. 1 times 3 is 3. And then we're going to add and get 0. And 1 times 0 is 0. And then we're going to add and get negative 10. And that is your remainder. And that's what we got when we just plugged 1 in. So P of 1 equals going to give you the remainder if you were to divide. All right, now what does that tell me about x minus 1? Tells me that since we don't have a remainder of 0, it's not a factor. So it's kind of like if I were testing, is 3 a factor of 7? Well, 3 goes into 7 twice, but it has a remainder of 1, so of course not. It's not a factor of 7. But 3 goes into 6 2 times, and it has a remainder of 0. So the remainder theorem says you can put your potential zeros in and just immediately, in the polynomial, immediately see what the remainder is going to be. But see, you don't really usually do that because if you're asked this question, you really want to know what the other factor is. But since this is not 0, then x minus 1 is not a factor, so we can't even do the second part. It's not possible to factor this polynomial with the given information because x minus 1 is not a factor. Okay, let's continue to look at another example. This is more like what you might have on a test. Consider the following polynomial. Use the remainder theorem to determine which is a 0 of p, x equals 2 or x equals 3. Then factor the polynomial as a product of linear factors with complex coefficients. Okay, so these are potential zeros. Now you can do this a couple of ways. You can plug 2 in and plug 3 in and see what the remainder is. But I wouldn't do it that way because we're then asked to factor. So synthetic division is actually more useful because it gives you the other factor. All right, and it's quick, right? So if I want to see if 2 is a 0, I'm just going to put 2 in the box and then the coefficients 1, -1, -14, and 24. And then I'm going to add and get 1 and then multiply and get 2. And then I'm going to add and get 1 and multiply and get 2. Then I'm going to add and get -12 and multiply and get -24. And then I'm going to add and I get 0. So right away, I know that 2 is a 0 because it's a remainder. But then it says factor, so we have to remember we started out with this x cubed polynomial. So when you divide by a linear factor, that's just going to go down to x squared, go down 1, so that's x squared plus x minus 12. So that's the other factor. And we have to turn that 2 into a factor. There we go. So now it's factored, but it's not factored completely because this is quadratic, and we have to see if that factors. And sure enough, x and x, the factors of 12 that subtract to be 1 are plus 4 and minus 3. So that polynomial says factor the polynomial as a product of linear factors. A linear factor, again, is a degree 1 factor. So all of these are linear factors. So that's it for that problem. All right. I never got to check 3, but it turns out 3 would have worked too. Let me demonstrate. So let's see if 3 works. 1, -1, -14, 24. So 1 comes down. 1 times 3 is 3. -1 plus 3 is 2. 3 times 2 is 6. -14 plus 6 is -8. 3 times -8 is -24. So sure enough, 3 is a 0, which we found right here when we factored. So this was, both of them were zeros. All right, see if you can think through number 2 on your own, and then I'll come back with the answers. Okay, so this time I did both of them with synthetic division. So I checked -3 and I got a remainder of 0. All right, I checked 3 and I got a remainder of 30. Okay, so that means that 3 is not a 0, but -3 is. All right, so then the next part, it said to factor the polynomial as a product of linear factors and complex coefficients. So dividing is a really cool way to factor. -3 is a 0, so x plus 3 is a factor. You started out x cubed, so this is 2x squared minus 5x plus 2. All right, now we have to see if this factors. So the previous lesson, sometimes I use the discriminant to see if it factors. So remember the discriminant b squared minus 4ac? So -5 squared is 25. B squared minus 4 times 2 is 9. So that tells me that's going to factor. So I'm going to go try and factor this quadratic trinomial. The factors have to be 2x and x, and then 2 times 1. They have to add to be 5, so that would be a -1 and a -2. So now I have completely factored this polynomial into linear factors. Okay, let's keep going. So there's a different type of question, and this one says finding all real exact roots of polynomials. Okay, step 1, if necessary, find the factor associated with the given root. If the root is a multiplicity of 2, then write the linear factor twice and multiply it out. Or you can use synthetic division 2 times, and I think I'll demonstrate that. All right. Step 2, use long division or synthetic division to reduce the polynomial to degree 2. Once you get a degree 2, that's important. We have the nice quadratic formula. So you want to try to reduce it to 2 if you can. Once you get it reduced to 2, then you're in good shape. All right, so here's what the example would look like. All right, so the first one says find all real exact roots. So that means you're finding zeros, you're finding solutions. That's what roots means. For this polynomial, if 3 is a root. So I'm saying that 3 is a 0. So if you have 1 0, you can find others, and it's a linear factor, or it's just a 0. So we put 3 in the box, and then 2, -11, 7, and 24. So we're going to bring down the 2. That's 6. Then add, and that's -5. Then multiply, that's -15. And then add, that's -8. Then multiply, that's -24. And sure enough, 3 is a root. You better get a 0 because it says 3 is a root. All right, now this gives me x minus 3, and this gives me 2. It goes down 1 degree, x squared minus 5x minus 8. So that's our polynomial, and we want to find, you got to understand the directions. We want to find all the zeros. So we know that one of the zeros, if you set this equal to 0, is equal to 3. Of course, we just found that. But how would we find the other zeros? Well, up here we were able to factor. Let's see if this is factorable. So -b squared, so that would be 25, minus 4 times 2 times -8. And see, it's not a perfect square. So this doesn't factor. That doesn't mean you can't find all the zeros. So how did we find this 0? Well, we set it equal to 0. That's how you find 0. So what we're going to do now is we're going to take that quadratic factor and set it equal to 0. And if only we had a formula that would help us solve for x. We do. It's the quadratic formula, right? So x equals -b, so +5 plus or minus the square root of parentheses -5 squared minus 4 times a times c, which I already did, over 2 times a, which is 2 times 2. So x equals 5 plus or minus the square root of, I already did the discriminant, square root of 89 over 4. And 89 doesn't reduce, so those are my other 2 zeros. So again, what we've just done, we found all the real exact roots. So here are my roots. We got a real rational root of 3. We have 5 plus the square root of 89 all over 4. And we have 5 minus the square root of 89 all over 4. And we want to leave it exact. And it might as well be a good time to tell you that. See, the degree of that polynomial is 3. You have 3 roots. Not a coincidence. The degree will tell you the number of roots if we account for multiplicity. Okay, let's do another one. Speaking of multiplicity. All right. So it says find all real exact roots for this degree 4 polynomial, but I'm telling you that -4 is a root, and I'm telling you that it's multiplicity 2. Okay, now these directions up here said to write this as a factor twice and multiply it out and then use long division. That's not how I'm going to do it. I'm going to use synthetic division. So this is pretty cool. So if -4 is a root, it gets to go in the box. And then these coefficients, 1x to the 4th, and then 3x cubed, then -36, x squared, then -176, that's the x term. Remember, I'm doing this because I can't skip. I have to put a 0 for if something's missing. But so far, nothing has been missing. Okay, and now I'm going to use synthetic division. And so 1 plus nothing is 1. Then we multiply. That's -4. Then we add. That's -1. Then we multiply -4 times -1. That's 4. -36 plus 4. That's -32. Oh, a little bit big here. -32 times -4 is positive 128. Okay, -176 plus 128 is -48. All right, I have a feeling I know what 48 times 4 is, but just to make sure, yep. -4 times -48 is positive 192. We have a remainder of 0. All right, so -4 is a root, so that's not surprising. Now, here's what you can do. -4 is a root with multiplicity 2. So that means you can use that -4 as a root again because it's multiplicity 2. So you can use it 2 times. All right, now we're going to do this again. There's no need to write the variables in yet. I will in a minute. We'll synthetically divide again. 1 plus nothing is 1. -4 times 1 is -4. That's -5. And then -4 times -5 is positive 20. That's -12. Then -4 times -12 is positive 48. And there it is again. So that's the cool thing about multiplicity is you can use it twice and it'll give you a remainder of 0 twice. All right, now we can't use that -4 anymore. But you started out x to the 4th, right? You divided by a degree 1. So this row is x cubed, x squared, x, and then the constant. Well, then we divided this x cubed by a linear factor. It should be x plus 4. And so x cubed divided by x, that's going to go down one more. So that's x squared minus 5x minus 12, which is our friend, the quadratic. And we know how to find the other zeros once we get to a quadratic. Set it equal to 0 and use the quadratic formula. You can see if it factors, but I have a feeling it doesn't. But we can use the quadratic formula, -b, so that's 5 plus or minus square root. -b quantity squared, that's a positive 25 minus 4 times 1 times -12 all over 2 times 1. So that's 5 plus or minus. All right, let's figure out what this is. 25 minus 4 times 1 times -12 is square root of 73 all over 2. Okay, so find all real roots. Well, we found them. We've got -4 multiplicity 2 and 5 plus the square root of 73 over 2. 5 minus the square root of 73 over 2. So remember I said the degree is 4, will tell you how many roots you're going to have. as long as we account for multiplicity. So you might say, wait a minute, degree 4, I only see 3 roots. Well, we have to account for multiplicity. We don't need to write it down, but we're just going to account it. So we're going to count that twice. 1, 2, 3, 4. So that works.